Hey guys, this is Ali with the AI Enthusiast, and today we're going to be talking about self-attention, how to code it up, so please follow along. Now, in the first video, we did the conceptual differences between self-attention and cross-attention. And so in this video, we'll actually be coding up self-attention, and in the next video, the third video, we'll be coding up cross-attention. Now again, this is all single head attention, in the sense that I could code up multi-head attention, but for now, every bit of code that you're going to see, it's all for single head attention. If you want me to make more videos and actually cover multi-head attention, basically multi-head attention for self-attention and then multi-head attention for cross-attention, please let me know and I'll make those videos as well. So that'll be like a fourth and a fifth video. But anyways, I hope these videos are adding value for you guys, and please like and subscribe. And thank you. Alrighty then, so we're going to be jumping into the coding portion of this. And on the left-hand side, you can see I put in Excalibur the actual equations. So this is the single head self-attention. Again, this is the encoder block. And then in the decoder, you have the cross-attention. So I'll be going through the self-attention first. Let's jump right into it. So over here on this side, we'll make it a class. We'll say single head self-attention. And if I'm not typing, I apologize. If I'm not typing correctly, I will fix it. So let's go ahead and make this a module. And the key thing to illustrate here again is the self-attention piece. But before I do any of that, let's go ahead and create the init. We'll do self, and then this is going to take in actually two things. There's going to be the embedding dim and then also the attention dim. And I'll explain that in a second. And of course, I always I always fail to do super.init. So let me just do that real quick. And then we'll do def and then forward. For any of these modules, you're going to need that. And then you're going to have the input data. We'll call this sequence data. And just real quick, this is going to be, you have your batch size. I know we didn't talk about it, but basically when you're training up your transformer model, you have a batch of samples. So your batch dimension, and then from there you have your tokens, number of tokens, or your context window, whatever you want to call it. I'm just going to call it time steps. And then basically on the last dimension is your attention dimension, or, we'll actually not attention dim, but we'll just say model dim. Or the other thing is embedding dim. So I'll just use embedding dim because I have that here. Let's go ahead. But basically embedding dim and model dim are synonymous. And yeah, so that is that, and we'll just do pass for now. Okay, so this is the high-level structure of our single head self-attention module. And on the left-hand side, you can see the self-attention block. Your data, X, is going to be batch times time steps times the dimension embedding. And basically, you have three matrices. So let's go ahead and initialize these guys. We're going to have self.wq, and you'll do torch.nn parameter. Just going to do torch.randn, embedding dim and attention dim. And yes, I know I can do, there are ways to code this up. This is how I'm going to do it. Self.wk, and it's going to be the same thing pretty much, or exactly the same. And then self.wv, and then I'll just copy that over. So now we have three matrices. The idea here is these are your weight matrices, right? And so this is just attention. You have your Q, K, and V. You have to multiply your data by your WQ, right? So that's in the forward pass. So these three equations. So let's just go ahead and do that. Over here, I'll do qmat, and we'll just do torch.matmul. And alternatively, you can use the at notation, and I'll show that in a second. But basically, you have your sequence data, and then you have your self.wq. And so I'll just copy this over. I'll do WV, and we'll just call this a K and this a V. So this is these three equations, Q, K, V. You have your data, and you're multiplying it by WK, WQ, and WV, respectively. Now, a key thing about torch.matmul, so I could have just done, you'll see a lot of online implementations doing this. So this is equivalent to doing that. If you want to use that notation, you're welcome to. One of the other things I want to mention here is it doesn't matter how many dimensions these tensors are. Matmul, or if you're just multiplying tensors it's going to take the last dimension So it's going to take, well, the last two dimensions. So sequence data is batch size, time steps, embedding dim, right? So you have time steps, embedding dim. Okay, so if I'm going to multiply this out, I'm going to then have, let's say WQ, we know this is going to be embedding dim x attention dim. That's what we just literally on the left-hand side, you can see that. So this embedding dim, it's going to ignore these like leading dimensions, and it's just going to take embedding dim, and it's going to look at, here's your matrix, this one right here, multiplied by this matrix. And you know, when you're multiplying any two matrices, the inner dimensions have to match, so embedding dims match. So the output of this operation, right? So I'm just going to delete this. The output of this is going to be a tensor, and it's going to be batch size, time steps by attention dim. Okay, so it automatically knows for each batch, like for each element in each mini batch or batch, for all the time steps, for each of those embeddings in each of those time steps or those tokens, right? Each of those embedding vectors, I want you to transform them into another vector using this matrix WQ, and this the dimension of this is going to be the attention dim. So that's what's going on, and that's happening for Q, K, and V. And so this intermediate like matrix, right, is the S, this is the attention matrix, right? So you just take Q and K and then you multiply them out. Key thing here, remember, Q is this, and then likewise K is this. So you have to ask yourself, well, how are we, like for each sample in the mini batch, right? For each of these in the batch size, how do we take n time steps with this vector for each time step, and then these other time step, like the same time steps, but you have a different set of vectors, your k vectors. How do you get an n by n? Well, you have to take these last two dimensions and you have to swap them. So if I swap this guy, attention dim, with time steps, now this matrix and this matrix, you can see the attention dim, the inner dimension matches up. So I'm going to multiply time steps by, so this matrix right here, I'm going to multiply that by this matrix here, the transpose, and all we're doing, the batch size is preserved. Remember, when you're using matmul, I can just, when you multiply this out, you're going to get back time step by time step. So that's what we're going to do right now. I'm going to go ahead and delete this guy. That was just for illustration purposes. Let's go ahead in the forward pass. We're going to do attention mat. And it's going to be torch.matmul. Same thing. You can use the at notation if you want. Qmat, right? And then you just have to do kmat. And we have to transpose, but we're only going to transpose like we showed in the previous example. And I just deleted it, but it's going to be, you're transposing the time steps with the attention dim. So this is dimension -2, and this is dimension -1. So I'm going to go ahead and swap those two out like this, and that should do it, kmat.transpose. And so this is effectively, now I've multiplied these out. Remember, the output of this is going to be batch size, by time step by time step. So I have now effectively replicated the S matrix here on the left-hand side. And so now I have the S matrix, I have to scale it. So this is going back to the research paper, if I can find it. Equation number 1. So you can see here, so then this is going back to the original paper. You can see attention. So once you have the Q and the KT, we just computed that. That's the S value. You have to divide by the dimension of the attention embedding, right? So we're going to divide by the square root of dk, and then we're going to take the softmax, and then we'll multiply by V. And that's really what we have here. We're just going to do a scaling operation here on the S matrix. So let's go ahead and do attention. Excuse me. I keep burping. So you keep your attention matrix, and then you're just going to do you're going to divide by yourself, and it's going to be attention dim. Remember, we captured that value as an input. So you need to know like what is the embedding size, and you need to know like what is the attention size, like dimension, right? So that's going to be as input. So you have attention mat and you have self.attention dim, and then you just have to raise this to the power of 0.5, like take the square root, and this will give you the this operation right here, the divide. Sorry, excuse me. You're going to divide QKT by the square root of D attention, and this gives you now this as scaled value. Finally, you have to take the softmax on this guy. So it's not too difficult. You're just going to do softmax result, and let's just do torch.softmax, and we'll do attention mat, and we'll do dim equals -1. And so you can see here, we're doing this on the -1 dimension, so it's across that dimension. Let's visualize that a little bit. So we have, we still have batch size by time step by time step. We just divided it, and then we compute the softmax on the negative dimension as you're going down. Yeah. So, and the reason why that is as you're going down, across each row, each of those how do I say it? Each of those vectors are going to be normalized. Yeah, that's how I say it. And so then, you know, when you do the matrix multiplication with the V matrix, you're going to get back a summation, like a weighted average of each of the V values that you computed, right? Because your V matrix, once you multiply this out, is batch size, time step, attention dim, right? So when you do this, you are effectively multiplying by the time step. So I can go into this more detail, but hopefully it's clear enough. Let's see here. Actually, we should go into more detail whenever we can. So we, per row, are computing the softmax. And so now if per row I'm computing the softmax, when I multiply this out, right? Hear me out, guys. When I multiply this out, when I'm computing the A, or the Y equals AV, so you're multiplying your softmaxed matrix by the V matrix, you're doing a time step by time step, that's the inner matrix, and it's going to be multiplied out by time step times attention dim, right? Remember, batch size we ignore, that's the outermost dim when we're doing this multiplication. So it's the rows times the V matrix, which is, you know, it's time step down, attention dim across. So you're taking a weighted average of each of your vectors. Easier way to look at this, I would say, is probably this operation, this article here. So you can see I have my n by n matrix. When I multiply by n by d, this going across, I've taken the softmax. So then, you know, you take across, you multiply going down. So then, you know, these are all value vectors for each of your tokens, and you're taking a weighted average. And that's really what's going on. Okay, that was very long and convoluted. I might edit that out, but, you know, at the same time, maybe not. But yeah, so over here you can see, you know, we have to compute this result. So let's just go ahead and do that. Let's just do new embeddings equals torch.matmul, and that's going to be your softmax result. I'm just going to copy that guy in there, and then vmat, right? So what we just did is softmax result. We know that that's this guy, and then we're multiplying by, if I just copy that over, and we just did it here actually. So I'm just going to clean this up a little bit. There we go. So you have this tensor multiplied by this tensor. And we know that torch.matmul will ignore the batch size dimension. So we are left with a batch size by time step by attention dim, right? Now that might look familiar, right? So we're saying that new embeddings is, you know, batch size by time step by attention dim. Okay, so that is essentially what it is. So we'll just return that, new embeddings. That is, we have completed our self-attention. And so now you ask yourself, well, okay, we have this, what is cross-attention? So cross-attention, if you look at the equations, it's actually the exact same equations, except the input sequence is going to be, there's going to be this, two sequences. So the first is like the same exact sequence data that you have, or the decoder sequence data, and then the second is going to be the encoder sequence data, what we had talked about earlier in the video. So I'm going to take a pause here, and then I'm going to get started on writing the other block. And that's going to be the cross head attention block.